Yeah, to have the microphone. Okay, so hello everyone, and let's welcome Aria. He's going to talk about today about boundary crossing problems and functional transformations for the Ornstein-Uhlenbeck process. So everyone, give them a word.
Hi everyone, thanks for the invitation. Essentially, this work is part of my PhD work I just submitted a couple of weeks ago. And this just got published last week as well, so it's kind of fresh. But because it's only meant to be like a short talk, I'll try to be concise and not go into details because the mathematical structure behind it is quite involved, and I can't talk about it here, but I'll try my best. So what's the whole kind of problem about? Okay. So say you have like a diffusion process, right? Anything that's going to continuous, a nice process on dimension 1. I don't know if you work with them much or not, but the most kind of fundamental one is the Brownian motion. I don't know if you know. But the problem is essentially like, say you have a diffusion process that starts at 0, it's continuous, wobbles, right? And then you'll have something which is like a moving boundary that has 0 is not 0, some sort of like a function in time, right? And you're looking to find the distribution or the first time this guy, the process hits this boundary, right? So if this hits this thing, then at this time in this one pathway, this guy is your t, which is the random time, it's a random variable. And it's the infimum or the first time you hit this curve, right? Now, I mean, like the whole thing is that like this thing is a moving boundary. So like the usual, like the classical setting, you have like a barrier. So if it's a line, things become much more simpler usually, but generally, if you have a function in time, it's a much harder thing. And why we're interested in this thing is because it has a lot of applications, right? Like in biology, as an example, the time that like a neuron kind of fires in your brain, it depends on like fluctuating kind of level that kind of reaches some sort of like a threshold, and then like the neuron gets released. It's modeled in this way. It's usually like a diffusion process that hits some sort of like a threshold. Or in finance, I mean, like the most easy thing is if you have a barrier and you have some asset, the first time you hit the price answer, right? But the problem, as I say, gets harder if this thing is not just a line, it's like a barrier. Even a line with a slope becomes hard in many cases, so I'll talk about that. So let's go to the easier setting, right? So what's the most kind of fundamental continuous process? It's the Brownian motion, right? I don't know if you work much with it or not, but it's just the most kind of fundamental mathematical object in the stochastic process, right? And the other important thing which you might kind of take away kind of from this talk is if your boundary is a smooth boundary, meaning like it's continuously differentiable and nice, then so we're interested in the distribution of this t function, right? And this thing is absolutely continuous with the Liouville measure, meaning there's a function pt that kind of describes like a density function of this t. So this t is a random variable, has a density, right? Then there is some function pt. Right? In the case of the Brownian motion, which is the most kind of fundamental thing, there's only essentially 4 interesting boundaries which that kind of pt is known explicitly. And this thing goes way back in time, not too back in time as well. So basically, Bachelier, like in 1900, in his kind of thesis, he proved the boundary a plus bt. So a line with a slope, in the case of the Brownian motion, has a very nice explicit kind of expression with the Gaussian function involved, right? Then, I mean, it goes ages after that. In 1967, with Breeman, he did some work on the square root boundary. Okay, so I mean, even when you have the Brownian motion, you only explicitly know the distribution of the first time you hit the boundary. When it's a line with a slope, or like which is like the Bachelier case, like basically Breeman, like the square root boundary like this, parabolic boundary as well is one. And then there's some weird log style of boundary, which was by basically Henry Daniels. So essentially, like the whole point is that there's not many boundaries which you can write this thing explicitly for when you even have the easiest kind of diffusion, which is Brownian motion. So the problem is a hard kind of classical problem. It's a thing which been kind of more than 100 years has basically time has been spent on, and not more really can be achieved. Even like an open problem now is the exponential boundary, or the reverse of it. What's the boundary that actually corresponds to the distribution of the first time you hit it being the exponential distribution? That's called like a reverse or like the inverse boundary problem. Even if you have the exponential boundary, apparently in kind of neuroscience has applications because like the threshold, which neurons like get fired, like the voltage reaches, it has some sort of exponential boundary. And in that case, like they don't even use the Brownian motion; they use the integrated Brownian motion. Even if you have the Brownian motion, you don't know the exponential boundary. It's like an open problem. So then you're like, okay, like you have like a few boundaries, 100 years have spent, not many progress. It seems that it's a very hard analytical problem. What can we do with the boundaries we have, right? So the idea is that, which was explored by my kind of supervisor and this other guy, is that say you have your boundary F, right? Is there like a transformation of it? So you have your boundary and then you kind of transform it with some kind of transformation that you can also talk about the first time you hit the new boundary. So if you know the distribution of the first time you hit the first boundary, meaning like the PT function. So this PT is a density function of the first time you hit this curve, right? So you have this F, and you know this function, which is the first time you hit it, or like density function, right? Is there some sort of like a transformation, like I'm calling it S applied to F, that you can still use the old kind of distribution function to talk about like the new curve, okay? And this question was explored in two major cases in a way. So for the Brownian motion and the Bessel process, we don't have to talk about what the Bessel process is now. There is this actually transformation, right? Which they showed that you can, if you have a curve that you know the first time you hit it, and then like you transform it with this. So if your F is anything, and you just kind of transform with this, and the beta is just a parameter, just a constant, right? Then you can talk about the distribution of the new guy. There is some sort of like a connection between the density functions with some like other functions. Like you will see how this thing looks like in a way. And then what they did is that in the case of the Brownian motion, they extended this. Like if you notice, like the beta here is just one parameter here. You can change the beta to anything you like. So if the beta is 0, you haven't done anything. Right? And then they changed it to the case when you can have an alpha. So you have a much more open kind of transformation, meaning you have this extra parameter that you can actually kind of play with. So only in the case of the Brownian motion, like this thing also exists. It's some transformation of the boundary. Okay. And then you're like, okay, what else can be done, right? We didn't really know much. That thing was done like in 2014 with Pierre Petit and Barbier. And then so we come to like the OU. Maybe I need to press it. Okay. So, I mean, you might know the standard OU process is like a classical process. It's essentially like the Brownian motion, but it has a tendency to come towards the mean here, like the case that the mean is 0. So how it would look like just like a diffusion process that kind of hovers around the point 0, but it can go long up or long down, right? So the Brownian motion, like the property it has, it goes to kind of plus infinity or to minus infinity. It doesn't have a limit, but it kind of oscillates everywhere, right? But the OU is this thing, which is very nice, and it has a lot of application because it's like the Brownian motion, but the further it gets from 0, it comes towards, and then it hovers around 0, right? And this process, I mean, probably in the 70s or 80s, they really liked it and used it in finance and stuff. But it's, I mean, like it's just like a classical process. I mean, there's some, so you have like the SD format is the minus KUT, or you can write the solution. And this integral, you can write it as a time-change Brownian motion. We don't have to think about this stuff now, right? Just the thing to know, like the RT is just some function. Like the RT is some function, and the SD is this inverse, right? They're just some functions. You don't have to think much about it, right? So again, like we just saying the first time you hit it, like the OU case is also interesting because, again, in kind of neuroscience, they also use the OU to talk about the same kind of fluctuation modeling. Or in finance, they used to use it a lot, but not really that much nowadays, probably. But it's just interesting from the point of view of basic mathematics, right? So again, well-known explicit results that exist is not much really. I mean, you have the hyperbolic boundary or the barrier. The expression, like for the barrier, is very complicated. So even in this case, right, if you just have a line and not a line with a slope, just a line, okay, the first time you hit it has that distribution. And that thing is an infinite sum of special functions, okay? And this thing isn't like an easy thing like to find. You can use, like there is like a theory in like diffusions that basically allows you to find the Laplace kind of transform of it, but then like to invert the Laplace transform isn't an easy thing. Anyway, but just so you get an idea, it's not an easy expression, right? Even if you have a line, like a line with a slope is also an open question. Like it's still not solved. So if you have a line with a slope, there's an expression that if you take the slope kind of constant like to 0, like you should get this guy. But we don't know it. Okay. Like the nicest expression that exists is if you want to hit 0 and you start not at 0. There's an expression, but other than that, it's just that. Again, like it's a challenging thing, right? So again, like this same idea, right? If you already know the distribution of the first sitting time of some boundary, can you find a transformation to transform it? Turns out in the OU case, it actually exists, and it's transformation which looks like this, right? It's a bit analytical, like it's maybe complicated looking, but the point is if you let the k to 0, like you get the transformation which works for the Brownian motion. This thing gets to 1, this RT goes to T, this thing kind of disappears, and you end up with 1 plus alpha beta T over alpha with your F. So there is some kind of structure kind of going on underneath there, right? Although the thing looks ugly, but it works, right? So just to maybe show you, you know, what's kind of cool about this guy from like a mathematical point of view, is that, yeah, there's some notation. I mean, like you don't need to bother with this. Like the tau is just an integral up there. Like if you see a tau, just know it's an integral, right? So just to show how many different areas of maths are connected in this problem, right? It turns out that this S guy kind of transformation has some connection with some ODEs, right? From just like a pure mathematical kind of point of view, right? And this ODE looks like this. Okay, so this guy is a complicated kind of looking ODE, nonlinear ODE, right? Like you have the double dash, you have it to the power of 3. It's just some equation, right? Turns out it has a unique solution, and the unique solution has these actual properties, and the tau is an integral function. And this SK alpha F actually for each alpha and beta spans all the positive solutions of this guy. So turns out that this equation, I don't know what it actually means, being honest. It's some equation which is connected. It's a very complicated looking ODE, but it has a solution. And if you use a complicated looking S alpha beta K transformation, which is for each alpha beta, because the alpha betas are just parameters, you just get like another solution of this guy. Okay. Maybe not that connected like to the original problem, but it's also a thing which happens underneath. But it looks ugly right now, so I guess I just kind of put it there just to show there's other results, and it's not only connected with the first time you hit it. And then the actual result, right, is actually this thing, right? Which again might look ugly, but the idea that I was telling you was that if you originally know this function, which is the density function, right? And then you like transform your curve, then it turns out that the density function of the new curve also gets actually transformed, and then you have some function behind it, which is in t. So essentially what happens is that your PSFF equals some function in t with the same actually transformation applying to the old kind of density function. So you have some sort of like a group thing happening underneath. I mean, again, like it looks maybe weird or nasty, but just kind of think of it like this. You just have a function, g of t, that's kind of before it, and then the same transformation applies on the density function. So both the curve or the boundary gets transformed, and the density function with the same kind of transformation function. I guess I have 5 minutes or something like that. So, I mean, as an example, right? Originally, like I told you, I mean, the proof, yeah, I guess you can also prove it from actually different techniques. Some are kind of quite analytical, some are quite probabilistic. So the first two are quite kind of probabilistic, right? One is you can use the concept or the technique which they use in the Brownian motion case, which was essentially like to use the Brownian bridges. It also extends to all your bridges, doesn't matter. There's another one which uses a lot of the algebraic kind of properties of this SK alpha beta kind of transformation. But the last one uses like the Lie group symmetries, which comes from a different area in maths, right? Which, if I had time, I would just explain it briefly, because only from this kind of Lie approach, which is essentially the PD approach, you get that the transformation is actually unique. It's the only transformation which exists that allows you to connect the first time you hit stuff. There's no other transformation in the case of OU or Brownian motion, like and all this stuff. So this guy like is quite special, and it only comes kind of from the PD approach, right? Maybe I would show you like the symmetries of what those even mean and stuff. But just as an example, right? As I said, like if you have a barrier, you had that complicated looking guy, which I showed, the infinite sum of special functions. But if you use a transformation and you have the freedom to pick your alpha betas, if you pick the alpha betas like to be 2 times k with k, which is like the parameter of the Ornstein process, you get some boundaries like that. So the A was a barrier, is we actually transform into like a moving kind of function now. And then you can use the theorem to show that the density that you hit this guy is like this guy. Again, it looks ugly, but it works. Okay, so like a barrier, right? It kind of gives you like the freedom, to make the barrier into some function in time. So you get like a moving boundary. With the alpha beta, you can also change it. So you get a big family of curves, right? Because you can change the alpha betas. That's just an example of like a few curves which looks. Right? I guess the last thing I wanted to show you was maybe like the symmetry guys, or maybe to what the hell they mean. Maybe you know, maybe you don't. I didn't as well myself, so I had to learn a bit about them. But the idea of the symmetry approach is that there is this like a fundamental kind of PD that governs. I don't know if you know much about like the Kolmogorov group, like the forward equation of a process, because it's a Markov process. It has like a generator as an example, or like the forward density function of it, or I mean like the transition density function solves the forward equation. And because the Markov process being stopped at the boundary is again a Markov process, the density function of it solves this PDE, which is just a forward equation of the process, and blah blah blah. But the whole point is that we will be interested to have a look at the symmetries of that kind of PDE equation, which is the first equation, which is just like the forward equation of the process, right? Maybe just to see like the cool thing about the symmetries is that if you have a solution of your equation, so if you have a solution of the of the forward equation, which is like the first PDE, right? How many ways can you kind of stretch or expand like basic space or time? So essentially, like you have a solution of it. If you, as an example, subtract like an epsilon of time of your function, it's still a solution of your PDE. But the symmetry kind of gives you all the different ways which you can kind of stretch or expand like your solution. So you have a PDE, you have a solution of it. What can I do to the function, to the time or space of the function inside, or like a transformation, that's still going to give you a solution of your PDE? I mean, as an example, like the number 3 one is just a constant kind of times your solution. So it always kind of solves with PDE. But anyway, you can use these kind of symmetries to kind of hidden inside find this SK alpha beta transformation. Meaning if you compose them in a very specific way, which also looks complicated, which means that you get a function which essentially kind of vanishes at the boundary. I mean, like it looks ugly and stuff, but I just wanted to kind of show you that like the PDE way, you can also find this thing hidden inside it. And essentially, it just kind of proves you that it's like the only kind of transformation which exists. I guess I'm almost out of time, I suppose. But essentially, that's about it. It's just unique, and that's it. Yeah.